So we are in this book right here, Generalized Linear Models with Examples in R, and we're just starting chapter 5. And in this video, we will cover, I hope to cover the first 3 questions because they all kind of just build off of each other. So in question 5.1, we are given different probability distributions, such as the beta distribution, geometric, von Mises, strict arcsine, and we're trying to determine which of these are EDMs. An EDM being an exponential dispersion model. In other words, does the probability distribution can it be written in a particular way? That particular way being, the definition of an EDM, basically. And so this question can actually be reasonably challenging because, so you push through, some algebraic manipulations, and you don't get to an EDM format, and then you think, was there some trick in here I missed? I don't know. And so hopefully I haven't messed up here, but it's completely possible. And so if you notice an error, then please let me know in the comments. Okay, so let's get into these. So what is an EDM? Well, an EDM is a probability distribution. So say this guy right here that can be put into this format right here. Okay, this is covered in the book, right? Where we have some function of y and the dispersion parameter phi taken to the exponentiation of y and what's called the canonical parameter theta, as well as a function of theta, and this is called the cumulant function, divided by phi here. There are other forms of the exponential distribution, expression here. This is the one that's given in the book, and so we'll try to see if these different distributions can be written in this way. Okay, so first up is the beta distribution, and this is a very difficult, or I mean not difficult. It's an unfortunate one to start with because you have to be familiar with what this beta function is here, or gamma function. I'm sorry. You use the gamma function to define the beta function, but whatever. So here is all of my math right here. And roughly the steps that I end up following throughout all of these is to take the log of the probability distribution, try to push the terms around until I get to something that I'm either reasonably convinced cannot be put into the EDM form, or it can be put into the EDM form. Now, the beta distribution here is just a little bit unfortunate because I think that the book would say that you cannot put this into EDM form, and part of that is because of, for lack of a better way of saying this, the number of parameters that are included in the beta distribution. But I think that I found a way here to just vectorize, what would otherwise be too many, and then put it into the proper format here. And so I think that this right here is actually probably an acceptable way to write the beta distribution. Now, in the next questions in 2 and 3, we are meant to answer some questions about the distributions from question 1 that could be put into EDM form. And I do not do the beta distribution going forward, but I think that it can be put into EDM form, but just using some vector notation. So, all right. So next up is the geometric distribution, a little bit nicer. There's nothing crazy looking in here. There's no gamma or beta functions. And again, here's my math. Roughly speaking, you can look at the steps yourself, but roughly speaking, I go through and I take the logarithm of everything so that things become, adding and subtracting. push through, push through, push through. And again, just to keep this video somewhat brief, I'll just rely on you to look at the math yourself. But in the end, I believe that we get an exponential distribution. Where did I put it here? It looks like I didn't completely spell it out, but I spell out the different terms that would go into it. So the A function is this, dispersion parameter is this, and you can piece it together. So okay, and so now we get into the Cauchy distribution here, so this is the Cauchy distribution. Oh, my cats are fighting. Okay, so now you again take the logarithm, push through, try to cajole it into a way that that gets into that form right there, and through your manipulations, or insofar as I can tell, you get to you'll maybe arrive at different forms, but I get to this particular form right here, and cannot put this into EDM form. Again, I hope that the math is clear enough that you can follow what I've done, and also identify any errors in case there was some trick that I missed that could have made it work. Okay, so next we have the von Mises distribution. So again, this is another kind of an unfortunate one, because in this case it relies you to know what the modified Bessel function of order 0 is, which is something that I had to learn a little bit about. I had no idea what this was. I'd never heard about it, but there's a little bit of information about what it is here. But the moral of the story is that we can't put this into EDM form. I'd maybe suggest reading this a little bit just to get a sense of what this modified Bessel function is. Okay. Finally, the strict arc sign. So this is the strict arc sign distribution right here. Again, this is a probability distribution that I was not familiar with. But we can go through and just do some manipulations here. And actually pretty quickly we see, well, when we just look at this, we see that it kind of looks like it already has some of the components that could be, that could easily fit into the EDM form. We're exponentiated. We have, a guy out here that, is not being exponentiated, whatever. But you can go through and show that you can put this into EDM form. Okay. So again, hopefully you can walk through the math for yourself. Now, in part, or in question 2, we're supposed to use some generic results about EDMs, namely that the expected value of the data is the first derivative of the cumulant, and that the variance is the second derivative. That's supposed to be, well, that's supposed to be phi. I think I must put sign there, but that the variance is at least a function of the second derivative of the cumulant function. So for those distributions in question 1 that could be put into EDM form, which I am using just the geometric and the arc sign distribution, we're supposed to find the mean and the variance. Okay. So first, on this first part here, I just go through and find the mean and variance for a generic EDM, right? And then later I will apply that to the specific form for the geometric and strict arc sign distribution. Okay, but for the generic discrete distribution, it turns out that I find the mean and the variance for discrete and continuous EDMs. It turns out that they come out to be the same, but the math is just a little bit different, because in one here I'm using summations, and for continuous ones you're using integrals, but that's okay. So the way that we go about tackling this, or one way that we can go about tackling this, is to find the different moments for these distributions. I believe that the reason that I'm doing it this way is the book discusses doing it this way or alludes to doing it this way. And so to find the moment generating function of a of a distribution, we take the expected value of e to the t y, okay? And so we're making up the value t here. We're just putting that in there, and then y, of course, is our data. All right. And so what does that look like? Well, to take the expectation of a random variable, here our random variable is e to the ty. Well, then I put the value of e to the ty, right? So y is changing, therefore e to the ty is changing. And then I multiply that by the probability of that y occurring, and then I do that for all y's, right? And that gives me eventually the mean, or I'm sorry, this gives me the mean of e to the ty, right? And then we will use that then we will find moments that correspond to the mean and the variance. All right. So again, I'm not going to go through every step here, but again, we already have e to the ty, and for the probability distribution of e to the ty, we put in the EDM, which is the probability distribution of a generic EDM. And then this is just mathematical manipulations. Hopefully you can follow all of the steps. But eventually we get to the moment generating function being this guy right here. Okay. And now to find a particular moment, call it the mth moment, where m is 1 or 2 or whatever, we take the mth derivative of the moment generating function, setting t to 0. Okay, so I hope that makes sense, right? Now we could go through and find the first and second moments, and then kind of manipulate the first and second moments, to find the mean and the variance. Again, where the first moment is the mean, and then the second moment minus the first moment is the variance. I think I don't have it written down in front of me, but there's also an alternative that we can use to find the mean and the variance, and that is through the cumulant generating function. Okay, where the cumulant generating function is the natural logarithm of the moment generating function. Okay, so when we do that, then we get a cumulant here. So the first cumulant is the mean, the second cumulant is variance. So just like for the moment, when we were finding the first and second moments, we take the derivative, setting t to 0, and that gives us the moments. Similarly, to find the first and second or third or whatever cumulant, we take the derivative of the cumulant generating function, setting t to 0. Okay, and then we don't have to do any further manipulations. The first cumulant is the mean, the second one is the variance, and we can just push forward that way. So here, applying that to our generic EDM, right? So I want to find the mean. Well, that's the first cumulant, which is the first derivative of the cumulant function setting t to 0. So I take the derivative of my cumulant generating function setting t to 0, and you can hopefully follow the math. And in fact, we get that the first. This is just proving that the expected value of y is the first derivative of the cumulant. Okay, and then similarly for the variance, now we just take the second derivative of the cumulant generating function, push through, and we get that guy right there. Okay, just as promised above. All right. So we just did that for the discrete case. The continuous case, I'm not going to go through in as much detail. Not that there's much detail being provided, other than you reading the math here. But now we're just using integrals instead of summation signs. But when you come all the way down to it, having done all of that, you get. I guess I just leave it right there. You get just the exact same moment generating function. Right, and because we have the exact same moment generating function, then we just take it for granted, so we get exactly this. So the rest of this I'm just not doing again because, finding the moment and the cumulant, etc., is just operating on the exact same expression, which we already did. All right. So now applying this to the specific distributions, which we found to be EDMs in question 1, all right. So we know how to find the mean and the variance, all right. So this is just some information on the geometric distribution, okay. And so all I'm going to do is plug in the appropriate terms to the generic, to our generic method for finding the mean, right? This guy, all of this stuff right here, which is just the first derivative of the cumulant. Where to go here? Right. So what is my cumulant function for the geometric distribution? Well, above it shows that it's this, and then we just carry through taking the derivative until we get to here, okay, where we have 1 over 1 minus e to the theta, and also from our earlier analysis, even though I don't point it out in this video, it's up there for anyone to read, but we find that theta is this guy right here, and so we can put, for anywhere where we see theta here, we can put the natural log of 1 minus p, which is putting it back into the parameters that are given to us for the geometric distribution, and push through, and we find that the mean is 1 over p. Okay? And then similarly, well, not similarly, but carrying on, to find the variance of y, now we're just taking the second derivative of the cumulant generating function, which is just taking the first derivative of the first cumulant, right? So I just take the derivative of where we ended up last time, right there. Okay, and you can push through, and eventually we get, an expression that is, just full of, our canonical parameters, which we already said was natural log of 1 over p. We plug that in, and just find what our variance is in terms of p, and it's right here, 1 minus p over p squared. Okay. So now moving on to the strict arcsine distribution. I won't. I'm not gonna. So now that you understand what the steps are here, I just have an abbreviated version here for the strict arcsine. Okay. All right. So we know what the cumulant is. We know what theta is, so on, and then we just find the first and second derivatives, and that gives us the mean and the variance respectively. Okay. And now finally, 5.3, we are to determine the canonical link functions for the distributions in 5.1 that are EDMs. All right. So first of all, what is a link function? So a link function, often denoted by G parentheses, where G, we're trying to figure out what G is supposed to be here. It links the mean of our regression mu to the set of linear predictors here. Okay, so how do we want to say this? So we are not saying the mean is a function. Well, how do I want to say that? We are saying that we are not saying that the mean equals our linear predictors, but rather some transformation of the mean is, our linear equation. All right, and so the book gives some examples of this. Okay, but for instance, in the Poisson distribution, which you can read about in the book, it is G here would be the log of mu, and it turns out that for a Poisson for a Poisson distribution, okay, I can't get out of this. There we go. That the log of mu is equal to the linear predictors, and there's others. Okay. Now there's only a few qualifications to be a bona fide link function, and namely that whatever this function is, it's monotonic and differentiable everywhere. Okay, and so this means that that you could swap in and out different link functions even though there's one that is called the canonical link function, which is often a very convenient one to use. You can switch them in and out. Okay. So then, what is the canonical link function? Well, the canonical link function is one where this function, that this transformation of mu here equals the canonical parameter. Okay. So I feel like you kind of have to dig in a little bit for. I mean, I'm sure that makes sense, but why that's an important thing, but or a convenient thing, I should say. So anyway, so for the geometric distribution, we go about finding this by taking the relation. So again, what we're trying to find is the canonical link function here, and so one way that we can do this is to say, okay, well, we know that g of mu has to equal the canonical parameter here, theta. And well, what is theta? Well, theta is, we already found it above, it's the natural log of 1 minus p. And then we put that in terms of mu and just continue to push forward, right? Because at the end we want g of mu to be in terms of mu. And so then it turns out that this is g of mu for the geometric distribution using the canonical distribution, or the canonical link function here. Okay, so it's the natural log of mu minus 1 over mu. Okay, and again, we just found that by assuming the relationship g of mu equals theta, and putting theta in there, and then solving for mu. Okay. Now, also for the strict arcsine, it's the same thing. Okay, so so we have g of mu. We set that equal to theta, and then try to, and then we know what theta is here. It's the log of p, and then we just push forward, solving for this in terms of mu. Okay, so I hope that makes sense. Sorry. Going back up here, so how do we know that this, that 1 minus p is this right here? Well, it's because we could also find what p is in terms of mu, right? So we knew that mu was 1 over p, right? We already found that in question 2. Mu is 1 over p. So then we can just find p in terms of mu. Okay, and similarly for the arcsine distribution, right? So then when I have p here, or when I have mu or p, I can kind of run the substitution until I get the second expression in terms of mu. So, okay, we will call that good.